All right. Welcome to Precalculus 1. We are officially starting. So the first thing we have to discuss are functions. These basic building blocks that we use later on in calculus and all other math courses. And these functions will be mathematical models that will mathematically describe phenomena that we encounter every day. So you have functions that will represent how to charge the battery for the phone, let's say, or the function that will explain how to describe anything that's happening in engineering or physics or biology. So there are mathematical models everywhere. And we are going to work on word problems that have those mathematical models, but we're also going to take a look at relations that are not functions. So we have to start somewhere, understand what the function is, even though you had a little bit of a preview in algebra course about this. And then we're going to learn the details about the function, domain, range, intercepts, and so on. Learn how to graph them. And all of our course, PreCalc 1 now, is going to be concerned with learning things about functions so that we can use them in Calculus 1 where it becomes very important. So we're just going to upgrade Calc 1 on top of this. It's not going to be course from scratch. So we start with the definition of a function that you must know at all times, because understanding the definition of the function is going to be crucial in you knowing what is a function, what is not a function. And then also how to relate what we write in mathematics to what we see out here or out there. So we start by writing that function is a rule. Which assigns to each x in the domain a unique y in the range. And we are going to underline words rule, domain, range, and the word unique is going to be underlined twice as the very important word. Otherwise, we would underline 5 times. So now we are going to take a look at the meaning of these words and then understand the statement as a whole. This is going to be the crucial concept of Precalculus 1, Precalculus 2, and then Calculus 1, 2, and 3. There is no calculus without functions. Certain parts of calculus can be done on non-functions, but majority of calculus is done on functions. And if you are not able to spot what is a function, what is not a function, obviously the entire calculus sequence is not going to go well. So we start by understanding this statement. Now, you will need to know this statement, and as I said last time, it's going to be one of the questions on your first test, possibly second or third, possibly final exam. 4 points. It needs to be stated in this fashion, without dropping any words, without changing the meaning of the statement. This statement means exactly what it should. And let's see what it is. So we have 3 words that are underlined once. The rule. And the word rule refers to a formula of some kind. So if I say y equals x plus 5, there is a rule which is different than y equals x squared, which is different than y equals sine x or anything like that. So the rule, word rule, refers to a formula that you can write down. So let's just do this and say formula. That's very, very simple to understand. Now, domain. Domain is going to be set of all possible input values. Set of all possible inputs. And range is set of all possible output values. Well, no, it's just a set of all outputs. There's no reason for word possible. So set of all output values. Now, guys, you are familiar with this concept in, as you would say, real life, right? I hate the phrase real life because this over here is not fake life or imaginary life. You have the situation where you guys get to see a product at the end. So think of a factory where the raw materials come in. Factory is going to put all of those raw materials together, and out comes the product. So it doesn't matter really what is that you guys are making. It is the whole process is the idea. So think about this. Let's take an example of something that it's being produced. Give me an example. Like whatever. Factory produces what? Cars. Very good. So what is the set of all possible inputs that you could have? Well, it's going to be raw materials like aluminum and steel and rubber for tires, right? So the factory is going to take and build the engine and build all of these things, right? But also leather for seats, right? And all other things that might be necessary to produce a car. So you will have domain is going to be set of all of those raw inputs coming into the factory. The rule of the factory is to turn those into cars, and the output is going to be arranged because you are going to make different types of cars, depending on which company, right, is making the cars. You're going to have all different types of cars on the all different colors of the cars, all different features of the cars that are installed or not installed, whether it's right the premium package or not. So you are going to have multiple things in domain coming in, a rule that changes those into the output, and in the output you are going to have the results that you get from the process. Now, the word possible appears in the domain, but it does not appear in a range. Possible. Now think, you are building cars, right? Good. So let's ask some questions. How many snails do you need to build a car? All right, how about jelly? None, all right. You get the idea, right? Possible inputs are going to be those that are relevant to the problem and can be used to build cars. Now, I haven't heard anyone use snails or use jelly to build cars. If they do make it, I'll have to change my example into something else. Possible inputs, exactly the stuff that we need to use in order for us to actually get, oh, thank you. In order for us to actually make the product. Cool. Now, word unique. Don't you expect that every single time when you use same components, you get the same thing at the end? Right? No? Why not? So you use all of the components that you need to make a car, you will be making the same car over and over and over again. Because you have the rule, which is the prescription, that you follow to make the car. So there is no way that you can get same components and build a space shuttle, because it doesn't work that way, right? You have exactly the number of, I mean, that's IKEA on a side, all right? One thing on the paper, one thing in a box, the third thing, right, what it should be. Right, you put that aside. If you're building a car, a little bit more detailed, right? So you get all of the components that you need for the car. Every single time you put those components together, you're going to get the car. Well, we'll get to the light switch over here. What's going to happen? What's going to happen? Huh. Who would expect that, right? Now let's repeat the experiment because something else might happen, right? Nope. Again. And I can stand here until the end of my days doing that, and it will be always the same output. Why? Well, think about it. Here is the X from the domain, which I used, right? I can use others, right? I can use nose. So that's our domain X. All of the things under the sky that I can use to flip that switch, that light switch. That's going to be the main. The function of that switch and the rule is that anytime I touch it, it is going to control these lights here. I don't have to worry about causing a major earthquake anywhere. I don't have to worry about starting someone's car with it, because that is not the function of that switch. If I want to create a device that causes earthquake, well, I have to build a device for that, and when I flip that switch, we cause the earthquake. That can be done, by the way. Also, you can rig your car keys right into that thing. If you have the car sufficiently close, you flip that switch and it turns the car on. It's all good. You can rig that. But in this particular example, the function of that switch is to control these lights. And that's its unique purpose, because there are other lights in a room, there are other lights in a hallway, there are other lights somewhere else. In Ecuador, more lights, all right? But this switch does not control. So uniqueness is extremely important. It is the word unique that makes the function, not the word rule. Rule is a formula, and we are very soon going to see that x squared plus y squared equals 9, which is a circle, is not a function. But x squared plus y squared equals 9 is a rule. It's a formula. So uniqueness has to be observed at all times. So here's a little graphic here. We have the input variable x going into this factory f, which is a function, and the output is y. So we have this understanding of what we're doing. And then we can also represent that using the two sets like this, where you have the input value x, and that gets mapped into the output value y. We are going to call this set domain, going to call this one range, and we're going to have them mirror images like this. So move x's from sets of x's into sets of y's by changing them using the function f. Now the notation that we are going to use is going to be y equals f of x. This is read y equals f of x. And it's not a multiplication, it's not f times x. It is x is embedded in f. And the quick example would be y equals x squared minus, let's say, 3. So if you quickly take a look over here, y is a y, equal is equal, and then this x squared minus 3 is the entire f of x. Now, just on the side, I'm going to say y equals g of x, and I'm going to have y equals, I don't know, 2x plus 7. So if I want to introduce another function, well, I just changed the name because f was taken by this one. So if I have multiple functions in the same problem, which will happen frequently, we are going to assign different letters to the different functions. Now, we will clearly, from problem to problem, recycle f of x every time. But within the same problem, if you have multiple functions, it will be f of x, g of x, h of x, and so on. And this notation here shows us what is the input variable, and the function will operate on that input variable to change it into a y. So if I plug in 1 over here, 1 squared is 1, minus 3 is 2, negative 2. So we have that y as the output is negative 2. So further examples, if I have y to be f of 1, that's going to be 1 squared minus 3, which is negative 2, which gives us the output as negative 2. We can also go y equals to f of 5, in which case 5 squared is, very good, minus 3. Awesome. I gave you enough time.
You did.
For calculations, it's a very ugly 22, so I'm going to make it better, a little bit better. So those are my, f of 1, f of 5. I can also get g of 1, g of 5. So we can go y equals g of 1. In this case, 2 times 1 plus 7 is 9. And y equals g of 5, which is 2 times 5 plus 7, which is very good, 7. Now, I'm going to circle back and talk about the idea of possible input values. So as I said earlier, if we, feed the snails into the factory that produces cars, it's not going to go well, because all you're going to have is infestation and bad smell. You're not going to actually make any cars because you can't make cars from snails. So if I do that, you see that the function actually breaks and the function doesn't work. So if I go with the next example and define my function y, which is also denoted as f of x, so either y or f of x, you can write one or the other. And let's say you say square root of x minus 3. Now from algebra, you should know already that you are not supposed to take a square root of negative numbers because, yes, the real answer does not exist. So mathematicians came up with what to spell that? I, which is the imaginary numbers. Very good. So right now, we see the problems above, and we understand that in the both examples up there, we can use any number to compute. Any, under the sun. But what about down there? Can I use 7? Yeah, I can, right? Why? 7 minus 3 is? And the square root of 4 is? Awesome. Can I use 103?
Yeah.
Why? How? 103 minus 3 is? And then square root of 100 is? Awesome. Can I use 2?
No.
Why not? Yeah. 2 minus 3 is negative 1. Square root of negative 1 is I, of course, but it's not real. So we are getting with this particular function already into this notion that, yeah, the answer might not be a real value, which is going to pose certain restrictions on our functions. So if I go here and I say y is equal to f of 103, we're going to get square root of 100 minus 3, which is square root of 100, which is 10. So we're all good with that one. But then if we say f of 2, that will give us 2 minus 3, which is square root of negative 1, which is not real. And that is a problem. Now, many branches of mathematics and many branches of engineering use complex and imaginary numbers. We are not doomed if we get them. It's just that for certain applications, we can't have them. I should not be getting into this classroom counting -7 imaginary students, right? It's not bad that -7 didn't show up. It's just that they're also imaginary, right? In which case I should go and check myself out, right? But the idea is with functions that we want to know what are the values, and that sits in domain. What are the values that we could use to get a real answer on the other end, and what are the ones that we cannot? And then there is another case. Let's go with, let's say f of x is equal to 2 over x. 2 over x plus 5, because we can, all right? 2 over x plus 5. Are we okay to plug in any value for x? Yes or no?
Yeah.
Yeah? How about 7?
Yeah.
Sure, why not? What's 7 plus 5? And 2 over 12 is 1 over 6. Awesome. So we can definitely use number, whatever I said, 7. There we go. Can we use 1?
Yeah.
Yeah, because it's going to be 2 over 6, which is 1/3, right? Awesome. How about negative 2? Negative 3? Negative 3?
Yeah.
Let's check. So how about negative 3? Is negative 3 cool?
Yeah.
Negative 3 is cool. Because 5 minus 3 is 2, and 2 divided by 2 is 1. Negative 2 is cool. Now you mentioned more than negative 5. Well, you mean less than negative 5, right? Yeah. So how about negative 15?
Just get a negative fraction.
Yeah, you just get a negative fraction. Awesome, that works as well. Does it appear that every single number you try works? No, why not? What do you mean it's uneven? Well, then we can have a fractional answer. That's okay.
Okay, is that a 5 or a 3?
That's a 5.
Then you're 5.
Why?
Divide the number by 0.
Nice. We get the see, gotta be careful. Awesome. So we can't divide by 0. Now I will explain why we can't divide by 0, which is one of the concepts that we have to understand. But because we cannot divide by 0, we cannot use negative 5 in this particular case. Obviously, when numbers change around, there's going to be another value that will not work. In this case, it's negative 5. So any number but negative 5 will work. So now what is the domain in this case? It's going to be negative infinity to negative 5 union negative 5 to positive infinity. This is a way for us to write using the interval notation that all numbers between negative infinity and positive infinity are cool except negative 5. And the only reason to discriminate against negative 5 is because it's going to create 0 in the denominator. And we are allergic to that one. We are allergic to 0 in the denominator. Now let's see why. It's going to be a live demonstration over here for you. It's not obviously going to be captured online because I'm not using camera, but pay attention and then hopefully you'll remember. So behold the group of 6 markers over here. I hope you all guys see. It's bad that it's three red and 3 green, but So I have 6 markers in this case. So as I hold these 6 markers, this represents number 6. Now, if I was outside, I would be holding 6 trees, but we're here, so I have to do this. So what I have 6 markers. Now, with these 6 markers, I can divide them into 2 groups. If I am dividing by 2, I am creating 2 physical groups. 2 physical groups. And everything that you do in mathematics must work out in what you call real life, and I'm really allergic to that statement, but I still unfortunately use it. So, let's go and divide number 6 by 2. I keep assigning to 2 different groups until I run out. 6 divided by 2 is how much? Well, each group has 3. This is the meaning of dividing. It is the oldest mathematical operation that exists. Not addition, not subtraction. Division is the oldest. Because people are always concerned with division. So we can now go and divide 6 by, let's say, 3. Very simple. You are now making 3 piles. You keep assigning to each pile until you run out. And then you just look how much each pile has. So 6 divided by 3 is clearly 2. Now hell breaks loose when you add another one. 7 is a prime number, right? And it's not divisible by any of the numbers that are lower than 7. Well, it's divisible by itself and 1, but yeah. So if you try to take number 7 and divide by, let's say, 2, you are creating 2 groups, and then you keep assigning markers to each group, and then there it is. If I put this one here, then this group has 4, this group has 3. So that's no bueno, right? If I put it here, Well, then this one has 3 and this one has 4. Again, not good. The only way I can divide 7 by 2 is if I break this one in half. But if I do that, someone will cry because someone forgot this marker, so I won't. And if I divide this by 2, let's call it as that, right? And then I get to assign half here, and we all know it's 3.5. When you divide 7 by 2, it's 3.5. That's the reason why. Now, I hope that you understood that dividing numbers in physical world just means create physical piles in which you are going to store stuff, and then you just count how many you have in each pile, and each pile obviously has to end up with the same amount of stuff. If you have leftovers, they get to be chopped into smaller pieces until they fit in one of the groups. That's it. Now, imagine if I am asking you to create, to give me the division by 0. Knowing that dividing by 2 means create 2 groups, 2 different piles. Dividing by 3, create 3 piles. Dividing by 4, make 4 piles. What is the meaning of division by 0? Create how many piles?
No.
0 piles, right? But can you do that? No, it's impossible. You already have 1 pile with all the stuff. You can't make 0 piles, right? You can't make 0 piles if you have already 1 pile. Does it make sense? I mean, I'm very good with that with pizza. I can make 0 piles like this. It's no problem, right? If you want me to show you how that experiment is done, just bring pizza in and I'll show you division by 0 like this, right? But in case of markers and physical objects like this, it doesn't really work. So now that we understand why, you should be always on the lookout for those zeros in denominators. Now, it was easy in algebra because you see it every time you get the slope to be 7 over 0. You say undefined and you're done, right? But the problem now is you're dealing with functions, these creatures that are higher in hierarchy. And you have to be mindful of the bad points. So you are not going to deal per se with 7 over 0. You will have to be aware that when you run into a problem that looks like this, -5 is not cool because it will create that situation where you could have 0 in denominator. And we don't want that because, as you can see from the experiments, it is not possible to divide by 0 because you can't take something that exists and create 0 piles and to divide into 0 piles. So there's no way for me to distribute 7 markers into 0 piles. Now, can you divide 0?
Yes.
Yes. As you can see, there are 0 cakes over here, and I equally like you all. You get the idea. Everyone gets a piece. It's a 0 in size, but again, it's thought that counts. Gotta love the language, right? I know. It's awesome. So, domain is the set of all possible input values. And you want to avoid 2 types of them. Those that create imaginary numbers as answers, and those that create zeros in denominator. The rest should be all good. Anything that provides the real number as the answer is going to be okay to put in as the domain. Range. Range is just going to be set of all outputs that you get. They're always real, obviously, in our case, because you pick the domain in a way that it will produce real answers over there. Awesome. So I hope that we understand function. Function is a rule which assigns to each x in the domain a unique y in the range. We understand that the values in domain have to be such that they actually produce the range. And we also understand that the values in range are always real because we pick the domain in such a way that it works. We also were very careful about talking about the difference between the word rule, which applies to formula, and since anything can be formula, the word unique is the one that makes the function work. Now, we're going to have 2 graphs here. Here's your domain, here's your range, right? Domain and range. And what I'm going to have here is the x1 variable and x2 variable. So these are the two distinct points. You can think as, I don't know, 3 and 17, right? So two different input values. And what's happening with these two input values? Well, those can each produce its own y output. So y1, and this one is going to produce some kind of y2. This clearly is a function because each x has its unique y. So we picked, I don't know, x1 is 7, and it produces 13 as the answer. x2 is 5, produces 29 as the answer, and it's all good. Now, what do you think about this one? You again have two input values, x1 and x2, but they map into the same y. So they had one y. Would something like this be a function or no? Is the uniqueness ruined? Uniqueness is not ruined, which means this is a function. Okay. It started like, no, it's not a function, but then it turned into, yes, it is a function. You look at x, and you see if it produces unique y. So this x produces only one y. This x produces only one y. So it's cool. All right? Here is the one that we can look at. How about this one? Now, do you get the difference between the two? So over here, uniqueness is gone. Single x produces two different y's. Now let's try and bring all of this to some kind of common sense. Guys, observe this. I'm going to pick at two students. You guys want to volunteer first? Let's volunteer your names, that's all. Taylor? I'm sorry? Maggie. Okay, so Taylor and Maggie. Taylor and Maggie. Who wants to be x1? Who wants to be x2? You want x2? Okay. So Maggie and Taylor, there we go. Guys, what is this y? This y is going to be this classroom, S246. You see that? So I can actually have, if you look in this classroom, we have exactly 40 people. We have 38 students. Raphael is here, I'm here, so that's 40 of us. We're people also. So 40. I can have 40 of these dots. Each dot will represent one person in this room. And we are all in one room. It is a function. Now look at this. Maggie, this is RVCC and this is your home. Ain't gonna happen, right? Unless you live here. And I know you don't because security kicks everyone off campus at 10:15. So yeah, I know. So we're going to take a look at these two, and we're going to understand that multiple inputs can produce a single output, and that is okay, where the single input cannot produce multiple outputs. This is what ruins uniqueness. So this one over here, not a function. Right? Uniqueness is not observed. You still have domain and range, obviously, and you try to use. Both of these are functions. They're both okay, and each one of those has the single output. So you have to be a little bit careful about those. So now let's bring this to the next level, where we start talking about graphing. And the first method for graphing is going to be the one that is the easiest and at the same time the most annoying of them all. This one can be used 100% of the time. It's very inefficient, and you really want to avoid it if you can. And the way we avoid it is we learn a lot of other stuff so we don't have to be annoyed. What is the method? It's the middle school method of plug and pray, right? You pick all of the x values that you want, you compute the y values, you have the points, and you plot the points, and you're done. Well, let's start with first the coordinate system so that we are all on the same page. I know you had algebra, I know you're in this class, but still, we should all be aware that there is the coordinate system here with the x and the y axis. X is the horizontal axis, y is the vertical axis. They meet at 90 degrees. Now, what these axes are simply two number lines from negative infinity to positive infinity. They contain all the numbers that we can think of. And they're actually the same, except one is vertical, one is horizontal. So this one, x-axis, starts at negative infinity on the left and goes to positive infinity on the right. The vertical axis starts at negative infinity on the bottom and goes to positive infinity on the top. In between, they contain all of the numbers that you can think of. Like, let's say, the first number you would think of, obviously, is like pi squared, right? No? All right, fine. Let's go with 1 in that case. So where is number 1? Well, it's right here. It's number 1. Number 2, number 3, number 4, and then on the vertical, 1, 2, 3, 4, and so on. So they contain all of the positive numbers. Now, obviously, 1/2 is going to be there, and number pi and pi squared and all other numbers that you can think of will be somewhere on those half axes. The negative values go the other way. So we have -1, -2, -3, -4, and then down -1, -2, -3, and so on. The point in the middle is called what? Origin. And the coordinates for that point are 0, 0. Awesome. So now what is the deal with this coordinate system? Well, origin is where everything starts, and then it branches in all possible ways. Then we have the axis with the points on axis. But guys, this takes off all of the space. You see that the entire sheet of paper is covered with this graph. I know it ends here, but the arrow says no, it's actually going to go forever. So this point over here also belongs to that graph, even though I did not extend the line all the way. So I can find any location on that graph. Now, this stuff is extremely important. How many of you use GPS? Everyone, right? You have them on your phones now. And if you look at the surface of the Earth from the satellite from above, well, it just looks like a flat plane. And it's all about the game of where the point is. You are going to be this little point, dot, that's going to go here, and then there, and then there, and then there, and then there. And the GPS is just trying to follow these little roads and the little lines that we drew, right? And we try to keep in between them, right, as we're driving. Because if we don't, we cause major trouble. So, didn't you ever think about that driving down the road? Like someone literally took some paint and just painted on the ground and then stick between those two. And you're going like, yeah, you'll check it out when you leave the classroom, right? You'll see them also in the parking lot. Like everyone is, except those experts who park in like three spots somehow. It's like, oh, experts. It's experts. Because I have no idea how you manage to park like in 3 spots with a car that's like wide for 1. But it's okay. Just stick around for long enough, you're going to see awesome stuff. Cool. So we understand the coordinate system. Now, this coordinate system, as you can see, when you draw these 2 lines that intersect, it's going to cut the space into 4 regions. Anyone knows the name from the class preps? They're called quadrants. So we're going to have a quadrant 1, quadrant 2, quadrant 3. By the way, these are Roman numerals. This is not qui. It's quadrants. And then we have the quadrant 4. So Roman numerals on this one. And they go into counterclockwise. So you start at 3 p.m. and then you go counterclockwise. And every one of your points that you can imagine will fall into one of these quadrants or on axis. So if something is on x-axis, it's not in any of the quadrants, it's on x-axis. So now, very simple. If you have a point, let's say point A, given as -3, 1, you will go -3, 1, which will be point A, and it's clearly in the second quadrant. So we have x to be -3, and at the same time, y to be +1. So you can see that the y value for this point is 1, because this is the y-axis, and the x value for this point is -3, and that's where the point A is. And in this fashion, you can trace any point on the coordinate system. This coordinate system is known as a rectangular coordinate system or Cartesian coordinate system. Why rectangular? Because any point you find by actually drawing rectangles. You see, if you draw this one from -3 up and this one from 1 to the left, they will intersect at A and they create this rectangle. So rectangular coordinate system. There's going to be a lot of cool stuff coming up in mathematics later on if you're interested. In Calc 2, you learn about polar coordinate system, and then you upgrade that into cylindrical and spherical coordinates in Calc 3. It's a lot of awesome stuff, which gives rise to hyperbolic mathematics, and finally you get to special theory of relativity, right? Oh, sorry, general theory of relativity. A little bit of, steps. There's about 6 years of math in between, but that's, It's like in movies when someone is getting ready, right? Everything is done in like 10 seconds, and then they're ready. Like, never mind, it's like, 5 years in between. All right, so we have all of that. And now we get to this basic idea of graphing using the middle school technique that works 100% of the time and works on every single problem that you can think of. So you all in algebra courses learned about how to graph the equation of the line, right? Y equal mx plus b, find the y-intercept, and then count the slope. But let's go first with the noob way to do that, which is pick x's, compute y's, and plot those. Let's say that your function f of x is given as 2x minus 3. So this is the way, this is the function. Now you see that I'm using this f of x rather than y. I'm going to drop writing this y very quickly in this class. So starting next time, which is Thursday this week, this year, I am going to stop dropping this y because f of x becomes our notation now. But you're familiar from algebra y equals 2x minus 3. The new notation for us in this class is going to be f of x equals 2x minus 3. And we are going to assign some of the x values. So let's pick, I don't know, -1, 0, 1, and 2, and then we become lazy. So here we have 4 values, and we are going to plug one at a time and compute y. So let's go. -1 times 2 is, -3 is, -5. Awesome. How about 0? 2 times 0 is? -3 is? Okay. How about 2 times 1? -3. 2 times 2 is? -3. There we go. So we computed all of these. Now, obviously, in this particular case, it's easy to compute. Wait for them to become, longer. Or how about if you have 2 ln x squared? You're going to compute that? No. You just want to know how to do that by hand. All right, so now let's take a look at the graph. The first rule of engineering is draw big. So if you have to use any kind of every kind of magnifying glass to look into your graphs, this course might be a challenge because you need to see how the graphing relations work. So start getting used to drawing large graphs. Also, I'm going to suggest a square notebook because lined paper doesn't have. You notice that my background over here is the square background, and that's for a reason because I have even divisions to the left and right and up and down, right? So those are, and they're important. If you draw the graph on a lined paper and it looks like this, and then your straight line looks like that, I don't think you get to learn much from it. It was considerably faster than what I'm about to do, but it's also useless. So then just don't even waste the calories on it. Just don't. If you're gonna do things right. Right? Like when they say no food or drink in lab. Right? So, what's the cool way to break that rule? You bring in steak dinner with steak knife and everything. Not like trying to sneak a chip under the desk, like no one will see it. Like, no. I'm talking like a paper napkin, right? Tucked in, full steak knife and a fork and a half a cow on the table. No, I'm serious. If you're breaking the rules, you break them in style. So over here, in this case, when you draw big. Plus, you don't want to embarrass yourself in front of them because draws good. All right, so -1 and -5. -1, 2, 3, 4, -5. This is the first point. It's -1 on x-axis, -5 on y-axis. Then the next one is 0, -3, which is on y-axis. Then we have 1 and -1, which is right here. And we have 2 and 1. See? Now, you are going to use the school ID or credit card or something to draw the straight line, right? You can also use a piece of paper which you fold 4 times so it has a good straight edge. I've been practicing drawing the straight lines my whole life, so I mean I'm really good with this straight. Look at my straight line, like amazing. I've been doing this over 70 years, so obviously it's going to be perfect every time. Mm-hmm. And there you have it. The cheapest possible way to graph any function, regardless of how complicated it is, in some cases you will need a calculator, is to pick x values. And if you pick x values properly, you will capture the essence of that function and you will draw. Now, I picked the function that you are familiar with because we can check this by using our algebra method, which is graph the y-intercept first, which is -3, and then go 2 over 1. Rise over run. 2 units up, 1 unit over. There you go. Magic? Yeah. Awesome. Next class, taking the rabbit out of hat. I know, step 2. We are going to study polynomial functions. Your linear straight line is in the family of polynomials. So this linear function will be around with us always. In Calculus 1, the concept of the linear function is going to be called the tangent line. And it's going to be one of the central problems of Calculus 1. And then that one will be eventually upgraded into tangent plane in Calc 3, which will serve the same purpose as tangent line in Calc 1, except this time in 3D space. So guys, you get to upgrade these things. We recycle them and upgrade them into higher level content, and you keep upgrading. This is the reason why I told you at the beginning of this class that you cannot miss any concepts from this class if you are moving on. If you're not moving on, just make sure you survive to this and you're done. All right? But for Calc 1, the question you will say, find the tangent line for the function so-and-so at point so-and-so. Good luck. Right? And then you say, what was the what line? Yeah, that one from algebra that you also already had in Precalculus, and now you're having it for the third time. So yeah, learn this stuff so you can go further. Next function. How about, I don't know, what are you interested in? What's your, anything? Remember, we can graph anything because we can just pick x's, compute y's. Anyone interested in any functions? Hmm? Sleep? What do you mean sleep? Hours of, oh wait. Oh, hours of sleep for pre-calculus class? It looks like this. It's a rapidly decreasing function. This is where the first exam is, right? You still think it's cool. Actually, whoa, wait, well, I can do better. So here you go, and it's where the first exam is, and then after that it looks like this. There you go. There's also a homework function. We use exponential model for that one. Looks like this. This is one homework per day, and then as you move with weeks, it exponentially grows up. You do more and more stuff. Talk to him if you don't believe me, right, Rafa? Of course, the project is here. He doesn't like the project. Like, he breaks my heart. Like, everyone's asking, why is the project so crazy? It's not crazy. It's application. It's cool. But why does it have to be 12 pages? No, it doesn't. You can make 15. It's okay. It's like, oh my god. No, that should be the happy times, like something that you casually do on Sundays. All right. Thank you for the input functions. I will go more in terms of, let's have the concrete example with x's and y's. So how about y equals f of x of, I know how much you love absolute value. What does the absolute value do? Makes every negative number positive. Great. So negative number 7 will become 7. Good. Negative number 7 will become? No. It will become 4, right? Negative 7 plus 3 is negative 4. Absolute value of negative 4 is positive 4, right? Yes, okay, good. It's called PEMDAS, order of operations, right? So, cool. Here are your values. Compute the y values and then graph them. Use your amazing OCD skills to make everything perfect and straight so that this stuff has meaning. Let's start with negative 5, negative 4, negative 3, negative 2, negative 1. Is this enough? That's good enough. All right, go. So what do we have, guys? Not a parabola. Parabolas are x squared, right? cheat off of your answers. For now. Hi. How's it going? Okay. Oh, okay. Now time to draw the. Yeah. Would you bet your money on it? Would you bet your money on it?
I might. I would.
How much are we talking now?
Well, I don't have much money. I'm a college kid.
Yeah, I know,
I had to buy
if
the
you had,
access code.
yeah, but if you had, let's see, what are we talking about? If you had,
I would put a Bugatti on it.
dude, nice, yeah, good, good.
Would I get a Bugatti back?
Yes. Well, whatever is here is there, so
Oh,
I can't really cheat. See?
true.
You love your Surface Pro. You love it. I'm like,
Yes. Of course, this is the best investment. You know, after buying food like this is the best.
Are you abusive at all with it? Like, can it
No.
handle it?
No, I'm not abusive
That's
type of personality. So,
but
but
this thing has gotten like stepped on and stuff, because this is stainless. That it can be. Whoops. I didn't step on it.
you get a bulletproof something for it,
yeah,
you should
right?
be good
like
to go.
Ice case.
Yeah, but these are the by far
They're
the best
so
pieces.
great. I went to Best Buy and was like playing with it. I almost.
Oh yeah. All right. So I hope you guys have the V.
Like that?
Just like that. That's exactly what you have.
I had it shifted up.
Oh yeah. Yeah, I'm not paying attention.
I was like, I guess I just lost my Bugatti.
No. Now you get two.
Okay.
Yes. At negative 3x, we have 0 for y, so that's the point at negative 3. And then we go into a V shape to the left and to the right. Now, it's very important, guys. It's very important to see that this one has a spike at negative 3. Because another function that looks like this, y equals f of x is x plus 3 everything squared, is going to have a u shape, which is a parabola. So if you curved at negative 3, for the previous example, it's wrong. So see, this one is curved. And the other one has a spike. Now, they are two different functions. So you can't argue with, yeah, it's close enough. Nope. It's like if you want a Bugatti and I give you, I don't know, come up with something like from 1938. And it's close enough, it's a car. Right? Like, you would argue, right? It's like, yeah, it's a negative 3. Sure it is. The other one has 4 wheels as well. Except you'll have to pedal probably most of the time. So the different shapes for different functions. And we are going to observe these features. What are the common features for all of the functions in terms of transformations? That's coming up next week at some point. So we'll discover all of those. Today we are practicing this basic idea from middle school, which is pick up your x values, compute y's, and then plot them, and then connect the dots. It's like a coloring book, except you don't have to color. That should be easier, right? No? Cool. All right, let me just check one thing in the textbook. Okay, so the next part that we would like to discover here is looking at the graph. How do we figure out the domain? How do we figure out the range? And also how to find x and y intercepts. And that will end sections 1, 1, and 1, 2. Then we have section 1, 3, which says more on graphs and functions. Sometimes it's very funny, but yeah. Okay, so what are the basic functions that you will memorize throughout this course? What are the basic shapes? Well, you all know y equal mx plus b, which is a straight line, right, the linear line. You will also memorize the square root of x, the 1 over x, e to the x, or exponential ones, the log ones. So they all have, and the absolute value, the v. Then it's going to be x squared, x cubed, and then the whole chapter on how to deal with those. All of them have input and output, which is the set of domain, set of range. So now, let's take a look at f of x equals to square root of x. F of x equals to square root of x. So what's going on over there? Well, what I'm going to do now is I'm going to tell you what it is, and if you don't believe me, you can check, because you know how to check this. Pick the values, compute the values, you will get the dots, and when you have the dots, plot the dots, and then connect the dots. Well, I'm just going to tell you, it starts at 0 because square root of 0 is 0. Any negative value before that is not going to fly with this function because it's going to give us imaginary. And we're going to have a line that curves and rises like this. So what are we going to do with this thing? Well, I am interested in domain, range, x-intercept, y-intercept. So I'm interested in these 4 concepts. And we're going to use these frequently. And they obviously mean stuff as you go down the line in mathematics. Domain, we explained that the set of all possible inputs. Now, there are 2 ways that are easy to understand, I hope, for you guys to figure out how to do these things. So the first way would be, imagine that there is a light all the way over here above the function. So the light is on the ceiling right here, and it's shining down. Domain will be the shadow, because domain is on x-axis. So domain is going to be the shadow that is created. Now observe over here, the light has no function to hit, so there is nothing on this side. And the first time the shadow is created is here, and there is shadow forever this way. So one way to figure out how to get this domain is to think of the light that it's above and look for where is going to be the shadow on the x-axis. So again, no shadow to the left of 0, because there's no line for a function anywhere. But on the right, there is a function, and it will create the shadow everywhere along the positive x-axis. Now I'm going to remove our light source and just simply say that the domain is 0. Oops, I gotta use the bracket. Come on, erase. to positive infinity, and we put parentheses. So these guys means include, and these guys means exclude. You cannot contain infinity, so we cannot put the bracket there. We can put parentheses. But 0 is included, so therefore we're going to have 0 there. So domain. Now, if you don't like the light analogy, and especially kind of tricky if you have also this kind of graph, and then, right, this is also going to be shadow, then you have another light underneath, and it gets to be complicated maybe, I don't know. So if you don't like the idea with light, you can use a simple piece of paper. I will use my keyboard. So what you do with a piece of paper is you cover the entire function, so you can't see anything, and then you start sliding from negative infinity to the right. And first time you see a function show, right there, that's your first point, which is 0 in our case. And then you can see that function is defined for all of these x's, exist, and it's going to go forever. So 0 to positive infinity. So to find the range, you can literally cover the function with a piece of paper and start sliding it to the right. And as it slides to the right, it will reveal the interval on x-axis. The interval on x-axis, so it's from x value to another x value, over which the domain exists. So for square root function, in this case, as you can see, is 0 to infinity. You do the same thing for the range, except now you get to slide up the paper, and you will see that the range is exactly the same, 0 to positive infinity, because range is set of y values. All of these y's are not taken by anything, because there's no line there, and then all of a sudden all of these y's have function associated with it forever to infinity. So range works the same as domain, except now you lift the paper up. X-intercept, well, that should be very straightforward. What is the point on the x-axis that line cuts through? 0, 0. I gotta reconnect the pen. So 0, 0. And the same for y-intercept. Again, 0, 0. So if you have 0, 0 as x-intercept, you must have it as y, because it's the only place where x and y-intercept coincides. Yes?
I just have a question about the domain and range.
Sure.
What situation would we not close?
Circle is not a function, but it does have domain and range. We talked about non-functions. I will be talking more about it. But since you asked, so not a function. So uniqueness is ruined, but we still have domain, range, and rule. So not a function, x squared plus y squared is equal to 9. Probably I'm the one of the best in the world at drawing the circle. No, I'm serious. I get it perfect every time. So you have a circle with the x and the y-axis, and since it's equal to 9, so you have 3, radius of 3. Domain exists for this. The range exists for this. And the rule, x squared plus y squared equals 9, which is the formula, exists. So 3 out of 4 words exist, but the uniqueness is ruined. Therefore, not a function, but still possible and exists in mathematics. And if you take the domain, your domain is from negative 3 to positive 3, and the range is also from negative 3 to positive 3. The x-intercepts are negative 3, 0, and positive 3 and 0, and the y-intercepts are at 0, 3, and 0, negative 3. Awesome question. Does it have to go to infinity? The answer is no. It does not have to go to infinity. So they can be contained. The ones that you guys are going to see in Precalculus 2, trigonometric functions, they're going to have their range between -1 and 1, let's say. Domain is going to be intersected for tangents and cotangents every pi, and so on. So there are going to be a lot of these. Plus, you can modify these in any way you want. Now, for most purposes in our class, infinity will be present in one or the other, but we can easily, as you can see, make functions. Oh, sorry, make relations that do not have domain and range. Do that. Great. Any other questions? You're all good? Everyone follow so far? Great. Awesome. Some of you are more concerned than others, but we'll get there, I guess. And or sleep deprived. I know, I'm guessing.
I was flying all the way. That's what I was late.
Do what?
I got off a plane.
Oh. At 2?
Yeah.
I was still awake at 2, yeah. Oh. All right. For a completely different reason. All right. What else are we going to talk about? So we understand how to find domain and range. Again, maybe I can show on a circle one more time this idea of sliding left and right. So again, you cover the entire graph, whether it's function or not, with a piece of paper. As you start sliding it to the left, you go nothing to see, nothing to see, nothing to see, and then you hit this -3. Aha, something. So it starts at -3 on x-axis, and all of the x values are cool because there is a line either above or below, or on both, and goes all the way until it stops showing up at 3. So domain slide from left to right, and record the values where it begins and when it ends. For range, go up. X-intercept, where does it cut through x-axis? Y-intercept, where does it cut through y-axis? The last concept is the concept of the vertical align test as the visual check whether the graph is a function or not. And basically what vertical line test says is that if the vertical line cuts through the graph more than once, the graph is not a function. So if the vertical line cuts through the graph, more than once, the graph is not a function. If the vertical line cuts through the graph more than once, the graph is not a function. So we're going to take a look at linear line. This is a random linear line. Here are my vertical lines. And as you can see, every time I cut through the graph, it cuts exactly once. By the way, I did not mention this before. I should. This is not a graph. This is a coordinate plane. The graph is the line that you draw on it. So if you want to know what the graph is technically this. That's the graph. Now we put the graph on the coordinate system. So make sure that when I say graph, I don't mean in any way at this. This is the set of coordinate axes or the coordinate system. There's names for this. The graph itself is the graph of a function or a relation, which is the line for the circle or the line. So anytime I say graph, I mean one of these guys, something like that, not the coordinate system itself. Another example, we can have our U shape. And if we draw vertical lines everywhere, so the first one, pass. Second one, pass. Because every time and anywhere you draw these vertical lines, they are cutting through the graph exactly once. And then we draw the circle. Actually, you know what? I practiced the circle, so let's. And now you can see that I'm going to draw just one, and you see that it cuts twice. So now why is this big deal? Well, look, single x produces a single y. This 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 x produces two different y's at the same time, which means uniqueness is ruined, which means the one at the end, not a function, just simply by looking at vertical align test. And that takes care of the sections 1.1 and 1.2. We learned the vocabulary, domain, range. We figure out how to find those. We'll do some calculations later as well. We have the x-intercept, y-intercept. We have the definition for a function. We have how to compute functional values by plugging those x values in. Being careful that the denominator is never 0, that the output is not imaginary and complex numbers. It's a whole bunch of stuff, right? Plus the vertical line test, graphing functions. There's been a lot of stuff, right? Welcome to Precalculus. All right? So we're going to take 3 minutes and 45 seconds break, and then 1.3. Go.